Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the IR spectroscopy with the help of some of the suitable example. What is the basic principle of IR spectroscopy, the technique, the interpretation of spectra, how to solve problem based on IR spectroscopy, as well as whatever the probable question, important question may appear in an exam, that kind of the discussion we were discussed yesterday. Today what we are going to discuss, let's see. Today we are going to study the Pmr spectroscopy. What do you mean by the spectroscopy? As we know that at the beginning, Introduction to Spectroscopy, one of the special chapter we have studied, and in that we have seen the basic thing required for that, or what are the parameters, or what are the units of that. This type of the thing we already discussed very systematically at the beginning in that chapter. The spectroscopy, let me define that definition once again. Spectroscopy means what? The interaction of electromagnetic radiation with matter is known as spectroscopy, and there are different spectroscopic technique available today, but at a T.Y.B level we are going to discuss only three basic spectroscopic technique, and each and every technique provides some of the information related to the organic compound. Part of the information provided by one spectroscopy very easily may not provide the information about the structure so easily by the another spectroscopic technique. In the systematic way at T.Y.B level, we are going to discuss three techniques, and these three techniques are very useful for structure elucidation or for structure determination of the unknown organic compound. And each spectroscopy provides us the information related to as a, for example, UV spectroscopy provides us the information about the carbon-carbon double bond present in the organic compound, whether that carbon-carbon double bond is present in a conjugated system or the isolated system. So that kind of the information we are getting very quickly from the UV spectroscopy. Similarly, it also provides information regarding as a stereochemistry, specifically geometrical isomers, means the restriction is a rotation is restricted due to the presence of carbon-carbon double bond and gives rise to different type of the isomer. That isomer is nothing but as a geometrical isomer such as cis isomer and the trans isomer, and that type of the information we are easily obtained from UV spectroscopy. It also throws the light on the stereochemistry. Just now we already discussed that one. And these spectroscopic technique we already learned by taking suitable example, and we adopt that technique. Second technique we have studied, which is IR spectroscopy. Again, IR spectroscopy is corresponding to or with respect to the functional group. As we know that there are different type of the functional groups available in the organic compound, and that definite functional group provide us particular absorption stretching frequency, and from that the organic chemist or the experts immediately come to know that by observing that peak in the IR spectrum, they easily identify what kind of the functional groups are present in the organic compound. And today we are going to discuss the PMR spectroscopy, and as we know that spectroscopy is nothing but as a interaction of electromagnetic radiation with matter is known as a spectroscopy, and the full form of PMR is nothing but as a, here let us see as a proton. P stand for proton magnetic, M stand for magnetic, R stand for resonance, that is a proton magnetic resonance spectroscopy, which is a PMR spectroscopy. It is sometimes it is referred as H1 NMR, and here again N stand for as a nuclear. H1 is nothing but as a proton, and N stand for as a nuclear magnetic resonance, which is the full form of NMR spectroscopy. NMR means nuclear magnetic resonance, PMR means proton magnetic resonance, and at a T.Y.B. we are going to discuss the PMR spectroscopy. Why it is termed as a proton magnetic resonance spectroscopy? The reason behind it, as we know that every organic compound involve hydrogen atom. In every case, that hydrogen atom present in every organic compound. Some of the exceptions are there in every rules. So similarly, here also, even though some of the compound do not contain as a proton, we cannot take the PMR study of that molecules such as carbon dioxide, because it does not contain the proton over there. Now The PMR spectroscopy, proton magnetic resonance, the phenomenon of proton magnetic resonance, PMR in short, was first observed in 1946 and it has been routinely used in organic chemistry since about 1960. The subject has grown so fast that it has become one of the most useful method for structure elucidation available to the organic chemist without the help of expert. When molecule absorb UV and IR radiation, the electrical component of the electromagnetic radiation interact with the molecule in PMR spectroscopy. We are going to study the interaction of the magnetic component of electromagnetic radiation with proton of certain atoms in the molecule of the, and hence the name PMR spectroscopy is given. Let me tell you here in a simplified way. In a UV and IR spectroscopy, the radiation of the electric component, remember here is the electric component, interact with electromagnetic radiation in the molecule, whereas in a PMR spectroscopy the molecule absorb the magnetic component of the electromagnetic radiation with the proton of certain atom of the nucleus in the molecule is known as PMR spectroscopy. The shorter, more energetic UV, here remember first point, the shorter, more energetic UV waves, lambda is equal to 200 to 400 nanometer affect the energy level of electron. This is the shorter, more energetic UV waves affect the energy level of the electron. This affect the energy level of electrons, whereas the longer, less energetic IR waves, lambda is equal to 2 to 16 nanometer, generate magnetic oscillation. For example, mechanical oscillation, for example, rotational, vibrational, in the molecule. In Pmr spectroscopy, the protons of an atom is exposed to very long, very long, low energy, that is low energy, I think lambda is equal to 1000 to 10,000 centimeter radiation known as radio waves. The proton is excited to higher energy levels, and the absorption spectrum so obtained can give lot of valuable information about the structure of the molecule. So once again, remember, these are the three important points which I have written on the blackboard. Number one, the shorter, more energetic UV waves, the range is given lambda is equal to 200 to 400 nanometer, affect the energy level of electrons. Remember, when UV radiation absorbed by the organic molecule, only electronic excitation takes place. As we already discussed this at the beginning in the introduction to spectroscopy, only electronic excitation takes place, and that's why we are getting the broad spectrum of UV. Why UV produce or gives broad spectrum? The reason behind it, along with electronic excitation, it is accompanied with vibrational excitation as well as rotational excitation as well as translational excitation. Associated with electronic excitation, we cannot obtain pure electronic excitation, and that is the reason Why UV produce broad spectrum of UV? That's the reason. Second one, that is, look at here, the longer as compared to as a UV, the IR has longer wavelength but less energetic IR waves. Lambda range is given, wavelength is given 200 to 1600 nanometer, generate rotational vibrational excitations. Generally, mechanical oscillation produce or generate when IR radiation is absorbed by the organic molecule. The vibrational excitation takes place along with rotational excitation is involved in it, and that's why we cannot again obtain pure electronic excitation, but as compared to the UV spectrum, the peak, the broad peak, here in case of the IR spectrum, it is sharper as compared to the UV, because here the longer wavelength but the energy is less as compared to this one. And as we know that the standard relationship between wavelength and the frequency, they are inversely proportional to each other, or the energy and the wavelength also they has relation, they are inversely proportional to each other, and therefore as the wavelength increases, energy automatically decreases. If the wavelength increases, energy automatically decreases, because they are inversely proportional to each other, and that's why that is the second point we have discussed over here. And the third one is a very long but low energy. The lambda length is given, wavelength is given here 1000 to 10,000 centimeter. Look at here the parameter or the unit in a centimeter. Radiation known as radio waves. Radio waves very long wavelength, but it is enough to excite. There is a nuclear excitation takes place, and how the nuclear excitation takes place, the detail of nuclear excitation we will discuss that in our coming lecture in future. But here just remember, very long, low energy, lambda is 10,000 to 1,000 to 10,000 centimeter radiation known as a radio waves, and the proton is excited to higher energy level, and the absorption spectrum so obtained can give lot of valuable information about the structure of the molecule. And that is the, I think, enough introduction regarding that proton magnetic resonance. The point which we are going to discuss over here, which is again very, very important one. What is that point? Let us see here the point which we are going to discuss. The basic principle of Pmr spectroscopy. That is the point we are going to discuss here. Basic principles of Pmr spectroscopy. That's the point we are going to discuss. Basic principles of Pmr PMR spectroscopy. Basic principle. What is the basic principle of proton magnetic resonance or the NMR spectroscopy? Most of the student not knowing the basic principle of the PMR spectroscopy. In case of the basic principle of UV spectroscopy, we have seen how that goes given the fundamental mode of vibration. In case of that UV gives how we can calculate as the lambda max, how the electronic excitations are occurred. Then second one IR, how the vibrations are produced by this one. And now is from here why some of the molecules are IR active, some of the molecules are IR inactive. There are two conditions there. If you remember those two conditions, from that we can easily, or the chemist can understood what type of the condition. Number one condition, the frequency of the IR radiation is equal to the frequency of the molecule. When perfectly matched, then and then that absorptions are recorded, or that is known as the stretching frequency or the group frequency, and that compound are the IR active. Another condition, essential condition for IR, whether it is IR active or IR inactive. Number second one, those vibration, those covalent bond possess magnetic moment. Do you know the magnetic moment? Magnetic moment, those molecules possess or has, they can produce or they can absorb as a IR radiation, and that compound are known as IR active. Those who do not produce magnetic moment, that molecules are the IR inactive. For example, acetylene, it is a linear molecule, it is a IR inactive. Carbon dioxide, which is also as a linear geometry, and therefore it is also as a IR inactive. But here the basic principle of PMR spectroscopy, here listen only one sentence forever, then and then you can understood the basic principle of the PMR spectroscopy. The PMR spectroscopy deals with the nucleus of an atom that possesses a magnetic moment. Remember, this is the essential and the requirement condition, necessary condition, or it is a basic principle of the NMR spectroscopy. The proton PMR spectroscopy deals with the nucleus. Remember, nucleus, every element. If you remember the long form of the periodic table, presently there are 118 elements are included, and every element has a nucleus, and that nucleus is very important as far as a proton magnetic resonance is concerned, or the nuclear magnetic resonance is concerned. The PMR spectroscopy deals with the nucleus of an atom that possesses a magnetic moment. Everybody knows the magnetic moment or the magnetic property. Magnet means what? That in the application of that magnetic property is very unlimited application of that magnets. Today, in day-to-day life, we are in every vehicle, the technologies in many industries, whatever machines are there, these kind of the technologies are used over there. In electricity also, everywhere that magnetic properties are playing very important role, and that's why these the basic principle of the Pmr spectroscopy. The Pmr spectroscopy deals with the nucleus of an atom that possesses a magnetic moment. The nucleus of an atom is positively charged and contains proton and neutron, as we know that. This is a nucleus which containing as a positively charged, which has proton and the neutron, and around that nucleus the electrons, suppose the minus, these electrons are revolving around that nucleus, but the center is known as a nucleus, and that nucleus further divided into that proton and the neutron. P stand for proton, N stand for the neutron. And the neutrons are electrically neutral, and hence the nucleus of an atom is positively charged and contain proton and neutrons. The neutrons are electrically neutral, and hence we are concerned with the proton only. As we know that these protons are positively charged and neutrons are the electrically neutral in nature, and therefore the nucleus, if you consider of any element, the nucleus containing proton and neutron, proton are positively charged, neutron are electrically neutral, and electron are negatively charged when that bond has a form. Remember here, like electrons, the nuclei of atom also spin about their axis. Look at here, the electrons, and they are positive, and there is a nucleus, and in a definite orbit the electrons are moving along in a definite distance of that nucleus. How these earth and sun and moon are revolving around themselves, or whatever are there, is totally based on this. Like electrons, the nucleus of atom also spin about their axis. This nucleus also spin about their axis. And the spinning of these positively charged nuclei generate magnetic field directed along the axis of spin. That is, these nuclei act like tiny bar magnets. Tiny bar magnet means very small piece of the magnet. If you go on cutting, the magnet always shows two. Suppose, let's see here, this is one of the magnet piece. One is showing as a north and the south pole. If you cut from the middle, from here, suppose, let us see here. Again, this will show north, south, and here north and south. If you go on cutting this, again smaller, here it will give north, south, then again is a north and south. That type of the very tiny particles in infinite pieces you make, still it shows the property of magnet, which is two poles. One is a north pole, another one is a south pole. This is the general property of that magnet. The spinning of these positively charged nuclei generate a magnetic field directed along the axis of spin, that is, their nucleus. Their nuclei act like tiny bar magnets. Individual proton and neutrons have spin quantum number, that is a plus 1/2 and minus 1/2, and therefore depending on number of nucleons in bracket proton and neutron nuclei also possess spin quantum number I. The spin quantum number I is a characteristic of nucleus. It is very important. The spin quantum number I, spin quantum number I is a characteristic of the nucleus, and all the nuclei that have spin quantum number I greater than 0, I is greater than 0, behave as a magnet. Behave as magnets. Remember, spin quantum number is a characteristic of the nucleus, because we are going to study concerned with the nuclei of the hydrogen atom in this particular case, and therefore proton magnetic resonance is playing as a very important role here, and the spin quantum number I is a characteristic of nucleus. All nuclei that have a spin quantum number I greater than 0 behave as a magnet, and therefore there is a magnetic and non-magnetic nuclei. First one is a magnetic and the non-magnetic nuclei. How magnetic and non-magnetic nuclei there are, if you remember, as a long form of the periodic table, there are 118 elements are present, and we can easily calculate whether that is a possess as a magnetic moment, that compound is a, that element is a magnet or non-magnetic property they are possessing. We can very easily categorize that one. But I think this is a basic principle which we have discussed here is over here. In the next lecture, we are going to discuss how we can categorize, how we can group, whether that are the magnetic and some of them are the non-magnetic. That are the thing we will discuss in the next lecture. Till then, let us stop today here. Thank you. Have a nice day.